Welcome to another episode of The Edge of Science. In today's episode, we're going to talk about radio signals coming from our universe. What are their properties? Why do we measure them? What kind of information can we get from them about the structure of our universe? Can they even give us some information about other intelligent beings in our universe? Today's guest is Dr. Wael Farah. He's a postdoctorate at Searching for Extraterrestrial Intelligence Institute in California, and he's working on detecting these radio bursts incorporating machine learning. Glad to have you here, Wael. How are you doing?
Thanks, Reza. Thanks for the opportunity to be on your podcast. I'm doing great. How about you?
I'm doing good with the typical lockdown at home and working from home, which we are built for, physicists.
Yeah, isolation.
So let's start general. What have you been doing during past couple of years? What have you been getting your hands dirty on, basically, in astronomy?
I'm technically defined as a radio astronomer. I have finished my PhD a few months ago, so I've defended my thesis 3 months ago. I was doing my PhD in Australia, in Melbourne, and I was using, the short story is I was using radio telescopes to search for millisecond wide bursts in radio that we'll, of course, talk about later during the show.
Cool, and congratulations on your degree. I know I'm sure it has been a hard ride.
A roller coaster.
Okay, cool. So let's just jump into the basics. What do we mean when we even talk about radio waves? What type of waves are they on Earth?
So radio waves are one part of the electromagnetic spectrum, right? So the light that we see, the light that our eyes pick up, are also part of the electromagnetic spectrum. Now, waves in general have a characteristic length, I would say. So a wave goes up and down. So we've got a wave motion, and so the wave has a characteristic length. And so the light that our eyes pick have a characteristic length that is in nanometer range, 400 to 800 nanometers. If you stretch this wave to a few centimeters up to meters and even kilometers size, you end up with radio waves. And so this is sort of a brief description of what a radio wave is.
So for our listeners, when we talk about wave length, the length of the wave two peaks, just imagine a water wave going in your yard or in a lake. There are peaks and valleys. The distance between the two peaks are what we are talking about here, basically. If you keep that stretching, it's going to become very, very barely visible. That's what can be our radio wave. So even on the water, if you start stretching that wavelength, they will become barely visible to your eye, right? So that's the same happens to the light. If you keep stretching it, it's gonna not be visible for our eyes, right? Now, why radio waves are very important on Earth? What kind of characteristics do they have that we enjoy using them actually a lot?
So the very interesting or the very important bit of radio waves is that they have a long wavelength. And so this means that radio waves can essentially be, they can traverse walls, buildings, and stuff like that. So if you have a radio, what we call a radio receiver or a radio, the tune that you listen to in quote unquote, hear radio. This happens because the radio waves can actually traverse through buildings and traverse through obstacles. And again, this is because it has, radio waves have large wavelengths. And so we essentially use radio waves to broadcast information to, for communication services, for, mobile phones, anything, you name it, satellites. So this is how we've been using radio waves for the last maybe 80 years now or so.
So when we say the wavelength is too long and they can pass through walls, let's talk about that a bit. Why can they do that? What is the characteristic of the matter that lets them pass through? Because there is something going on that they can interact with, right? That's why they pass over.
Yeah. So if the wavelength of light is comparable to the size of the object that it is encountering, the interaction would mean that the material can actually absorb the light, right? And so this is why wood, for example, is opaque to visible light, because as visible light hits it, the wavelength of light is small enough such that it can easily interact with that material, right? But because radio waves have really large wavelength, they essentially just do not see, in a way, they do not see the wood of block of wood.
Yeah, like if we look at it on the water as well, again, the water is very, for me, I like to put it on the water format, because so if you have an obstacle on the water and you have a very long wave, the wave which is very, short in the peaks, but it has very far distance from each other, those peaks. If you put a hole in something, right, it can pass through smaller and smaller holes, so easily, because it doesn't hit it. But if you go with a long turbulent wave, it's gonna hit that and stop and get weaker. So that's how I try to imagine it, and I think it's a good way for our listeners to imagine it that way. I understand it gets harder when you talk about matter in physics. Yeah. So when we study the universe as astronomers, we usually look at like different type of light, right? From optical to radio. Why radio? Like, why not? Why it's not enough to use optical in our universe, or use UV, or use X-ray? What's happening? Why do we care about radio too much?
Yeah, every wavelength of light tells us something. So every wavelength of light is a story on its own. So you mentioned optical. You can actually go all the way to gamma rays. So you've got gamma rays, X-rays, UV, ultraviolet. Then you pass through optical and all the way down to radio. Every single bit of the electromagnetic spectrum tells you something about the object that you're trying to study. Yeah, I mean, we can probably go into details in that.
Yeah, we will. So basically, opticals, when you look at the star, it's the optical. The sun almost gives us in every wavelength. So the sun that we have up there, people may think it's only, visible light. No, it is not, right? We can have UV, X-rays, so many other wavelengths is coming from that star, up to the lowest and the highest, the very large spectrum. Now, so when we look at radio, because there's also other things that radio has that other optical, as we talked about on Earth, they get blocked, right? So that means we can see short distances with them because they'll get blocked faster, right? Now, radio, is this the same in universe when we look at the radio signals, right? Can they come from much farther distances, not disturbed?
Yeah, exactly. So the same way that optical light can be blocked by a block of wood, same things happen in the in our galaxy, for example. In our galaxy, there's dust all over the place, right? And so dust can interact with optical light, for example. So as optical light, as light traverses through the dust, it gets absorbed. And so for us observers on Earth, we cannot detect this optical light, right? And this is why the Milky Way is seen as a white strip, because due to this interaction. Whereas things in the radio look completely different, because radio just ignores the dust and the matter that is, dust and gas. This is what we call them around our galaxy. So just radio waves just passes through, and then we can detect them sort of easily without.
So that means we can get more information from objects that are very far, right? Because they will not lose it to foreground objects or something in front of it that basically put when it comes. Now, so we know basically in our galaxy, the radio waves are, as you said, it shows a very different galaxy than people are used to seeing in optical. Right. So what kind of information the radio is giving us from in our own galaxy? Let's not just go out there. What can we get out of it to understand maybe any structural format or something that we haven't seen before? And do you know when did we start even thinking radio? In science, let's say, in observations?
Uh-huh. Okay, how about I answer the first question and then we move into the second question?
Sure.
So the first radio was built, or the radio telescope was built, I think back in I need to be correct about this, I can Google this really quick, but maybe into 1950s. And so the Milky Way galaxy was detected by mistake. And so the galaxy, our own galaxy, was detected in radio, and then a few years later, it was actually confirmed to be the Milky Way. And so here I want to move into your next question, which is, or actually I can give like sort of a broader use of radio waves here. And so many objects emit radio waves. They can emit radio waves over different emission mechanisms. A very common one is the continuum emission mechanism, which essentially means that you have an object that has a certain thermal property, right? And it emits light over the entire electromagnetic spectrum, right? The sun peaks at the optical because it has a the temperature of the sun is in such a way that the peak of the emission is around the optical wavelength. But as you mentioned before, the sun can emit over all the wavelengths, including radio. So the first way we can see things is through continuum emission. Another way we can see radio emission is through a mechanism called a synchrotron emission, which is when an electron gets accelerated around magnetic field lines. So when an electron gets accelerated, it loses energy in forms of radio waves, and it emits light. So this is another way we can detect radio waves.
So just before moving in this part, there were parts that I think we can go a bit deeper, not too much, right?
Yeah.
So when you accelerate electron in a magnetic field, we give the radio comes out. Why is that? Why it gives the radio energy out? What happens to this electron? Because it's just a negative charge going on its own in a magnetic field. So what do we mean? How does it get accelerated even?
Yeah. So magnetic fields and electric fields can interact with each other. And so you can imagine the electron, because it has a charge. So it has a sort of an electric field around it. And so the interaction between an electron or an electric field and a magnetic field means in such a way that the electron would accelerate. And so this acceleration just releases. I mean, we can go into the details of the physics here, but I'd probably bore everyone with this. But I guess the main point is an electron whizzing around a magnetic field line has the characteristic that it emits a wave, and the energy or the speed of the electron tells you dictates the energy of the emitted radio wave, or the wavelength of the emitted radio wave.
Yeah, in order to conserve some properties, electron has to emit those radio waves, right? That's the nature basically pressures electron to emit radio waves in that situation.
Yeah.
Now, the other thing we talked about was the concept of temperature and relationship of the temperature to the wavelengths that we see coming out. That may be a bit, maybe our listeners would not be familiar with why that temperature why it gives different different temperatures gives you different basically waveforms or wavelengths. This may be, if we can elaborate on that.
So this is called a black body radiation. And so again, we can go into details as much as we want to, but like the main storyline is as you start heating objects, so an object with a certain temperature, if you heat that temperature, the peak of its emission would shift towards shorter wavelengths, right? And so if an object is super cold, it would emit at lower energies or lower wavelengths, including, of course, radio. And as you heat something up, it will start emitting at higher and higher frequencies, or lower or shorter and shorter wavelengths. So yeah, I guess that's a short answer.
Yeah, I'll just give another, again, since we started using the water waves a lot, again, looking at, so since temperature has very direct relationship with energy, right? So why you see a heated metal? Because you're heating it a lot with a lot of energy. You're wasting a lot to make it heated. Same as the water. Imagine the water right now. When we talked about when there's not too much energy, the water is going to be barely visible. Now, when you start, smashing the water with something to make violent waves, so if it becomes very violent, the energy is going to increase. That means the wavelength is going to get shorter, or those peaks are going to get closer to each other. And if they hit something, they have more power, right? So that is how people can imagine, I think. Hopefully that's a bit clear right now, that how it relates to wavelength. Why when we say temperature changes, the wavelength has to follow. Now let's continue on where we were going. I hope we didn't deviate too much, because we were talking about the mechanisms of the radio.
Yeah. So back to our galaxy. Well, back to our universe here in this sense. Every object has its own nature and own temperature. And so once we start detecting radio waves from them, we can essentially study how the objects are. So a very, on the synchrotron emission, I can talk about, let's say, supernova remnants. So when a star goes kaboom, when it explodes, here in quotes, it leaves behind a supernova remnant. And so this is just the material that got shattered, let's say, or dispersed around the interstellar medium. And so this material gets shocked with the interstellar medium. And so this shocking creates pretty much electrons that are, and the magnetic field lines, they create electrons that are whizzing around magnetic field lines, and so they emit radio waves. And so we pick up that signal, we pick those radio waves, and we study supernova remnants, for example. So this is one thing. Another thing is the Milky Way galaxy emits continuum emission. So that continuum emission also, we can study the structure of the Milky Way galaxy. Another important, I guess here we did not mention, is that line emission. So electrons that go from an energy level, so when electrons are whizzing around their protons or their nucleus, if they go to a lower energy state, they also emit energy, or they emit energy in the form of light or electromagnetic radiation. And so this emission is called a line emission because it's a very specific wavelength. And so we can also use, let's say, the amount of this, or the flux, or the amount of light that we detect from a certain object due to these transitions, to literally count how many atoms there are in that object, for example.
Or what type of material you're looking at, exactly. Because there should be specific material, right, to give you this radio. Now, when we say we detect them, right, you said we detect them on Earth. So maybe our listeners would want to know, how do we actually go on detecting these things? Because, I'm sure we astronomers don't turn on our radios and then start listening to stars, right? So there should be some mechanism that is not that simple as it's thought of.
Yeah, a good analogy here, you said you turn on the radio. In a way, under the big picture, it's sort of the same thing in radio astronomy, but I can elaborate more. So in radio astronomy, we also use telescopes, okay? So telescopes are, a collection, let's say, of it's an apparatus that is made to collect as much light as it can. In radio, we use dishes usually. And so the bigger the dish, the more light it can collect. And so we use a dish. So the basic description of a radio telescope is you've got a dish that collects the wave, and then it focuses them to a certain point where there's a receiver, there's a detector. And this concept is pretty much the same in most of the astrophysical, or most of the wavelength range. And so a radio telescope works the exact same way. It collects radio light, focuses them onto a certain point where there's a receiver that samples the light, and then we turn this the signal. It's usually in analog, so we turn the signal into a digital signal, and then we do some processing on the data, and then we can do our radio science.
So there's just for our listeners to imagine. So if you have an internet, if you're in a remote place of a country, usually you should use the dishes to get the internet, remote dishes. So the concept is the same, but the dishes are gigantic, much bigger. And just the question is, why do we have to use this gigantic dishes? Because in optical, for example, telescopes, the mirrors, right, are 2 meters, max 6 meters, 8 meters. But radio, I'm sure you've seen them and you're close to one right now. So they are gigantic, enormous. And why is that? Why should we have a very large, telescope to get data?
Yeah, simply because we can. Essentially, the bigger the telescope, the better, the more light you can collect. And so you mentioned gigantic telescopes, but there are essentially 2 ways we can do radio astronomy. If you want, you want to talk about interferometry and single dish right now?
We can get next. I wanted to ask you next. Let's
okay.
talk about the first one. Why? So one would be cost, right? Because mirrors are damn expensive to make simple. But there is also, I think, it should be some other reasons that we need a bigger, area to gather data for radio.
Also, the wavelength of light has to do with it. So we need a bigger dish to collect the certain wavelength of light that we're trying to measure. But as you mentioned, radio dishes are relatively simple compared to optical, let's say, mirrors. Optical mirrors, you have to really be careful about what sort of mirror you put there, and aberration effects, and it's a bit complicated. Whereas with radio astronomy, all you need is some chicken wires, and it's fairly simple to be able to reflect, to be able to collect radio light.
Yeah. So, but sometimes you can go big also, because I think the radio waves are weaker. We have a lot of noise, by the way, right, on Earth, that is radio. Since, as we talked about, radio can go everywhere easily, we need to have a bigger telescope, because maybe the signal to noise ratio again became technical. So basically our signal, the one that we care about coming from the sky, we want it to be in proportion to noise we get from Earth, to be larger. That's why I think also the large part, I recall, would be important. And since you're right now close to one, the other thing that is interesting for our listeners to know, right now Wael cannot have his phone on. I am just to
I'm wired.
Can you talk about that a bit, that experience? I think it's very interesting, because I had to have it for 1 week, and it was funny because I couldn't use anything except internet.
The experience, I would say, I'll put it this way: I do it for science. But as you mentioned, because I literally live on site, so the telescope is 1 mile away from me here. I have to essentially have 0 transmission, so no radio, no cell phones. Everything needs to be off. I can't use Bluetooth, for example. No Wi-Fi. Nothing, pretty much nothing that can emit radio waves.
And the reason is because these machines are extremely big, and they are extremely sensitive, right? So as we said, when it gets bigger, it gets more sensitive. So, and when you're closer, it's going to amplify. You don't want to detect your conversation and call the aliens are connecting us, right?
Exactly.
now let's talk about the second way, because we can't go too big, right? There is a limit. I think the biggest one is the China is right now making that radio telescope. I don't know how big is it. Do you know exactly how many meters was there?
Yeah, it's a 500 meter
So just radius, right? Or is it
diameter?
Diameter, yeah. So for our listeners, just imagine a 500-meter diameter telescope. That's huge, which I think in the receiver, you can have a room for scientists to actually sleep and work.
Yeah.
It can be that big.
Yeah.
Now, let's talk about the second way, because we can't go as much as that. I don't think we can keep making it bigger and bigger. There should be a better way, right, to get a bigger telescope without putting too much money into it.
Yeah. So I can start by talking about the big dishes and how we can
sure,
go into the other way to do radio astronomy. So with these really gigantic dishes, what we usually do is we usually chop the dish into smaller pieces, right? So rather than having this massive mirror or the primary mirror like to be a single mirror, we chop them into smaller pieces. So there would be always some gaps in this radio telescope. Now, you can extend that, or you can extrapolate this idea by, rather than having the same dish that's being divided, just take those small pieces and just spread them in different places. And rather than having a massive single dish, have smaller dishes that are connected to each other in a certain manner. And this facility, or this instrument, is called an interferometer. So rather than having a single massive dish, we can chop this massive dish, make it into smaller instruments and smaller receivers, smaller dishes, and then spread them in space. That's another way to do radio astronomy.
So let's talk about that, because this is a very interesting one, for me at least. I know. So one just example for listeners. Imagine you're in your home and you have a bunch of very weak routers. You want to gather more internet, right? You can spread them around and strengthen the signal. And basically, because you're increasing the chance of getting all those signals, the radius of the house will become your router right now if you have multiple of them. So that kind of relates to the idea of having multiple of these things. And now, how big can we go? Like that is the question right now. How big of a telescope can we build using this interferometry?
Technically, with our technology, we can go, and it's already been done, of course. We can create a telescope as big as the Earth, as big as the planet.
Oh, wow.
Essentially, just have two instruments that are far away from each other as much as possible, make them observe the same source on the sky, and then do some processing. This is called cross correlation. So you multiply essentially the antennas together. I don't want to go into details here, but like what we can do is we can use this separation to make the Earth itself become a massive telescope. And so there's a small point that we did not talk about, is the bigger the telescope, or the bigger the dish, the smaller the spatial resolution we can get, right? So as the telescope becomes bigger and bigger, we can detect smaller and smaller objects on the sky, or we can have a better spatial resolution. And so this is what we do with the technique called very large baseline interferometry. So the baseline between those two elements of that telescope are really large as the radius or the diameter of the Earth, for example. And so, I guess that's the long answer to your question.
So when you make it, for our listeners, when the resolution goes higher, that means you can start seeing farther and farther in the universe and pinpoint the places that you're more interested to watch, to see what's happening. And the other thing I just want to clarify, I think, is like when we say there are two telescopes, they are arrays of telescopes, I think like 64, something like that, in one place, and a big gigantic one in Chile, another. So you connect all of these basically, right, at the end of the day together, and which is, I think, impressive, when it comes to science of it. Now let's get to like more, we know now we get to the place that how we detect them. Now, what do we detect with them? That becomes very important. As you talked about, we can start from very smaller telescopes, I mean, not that small, but to look bigger map, of the sky, or start pinpointing on very, very important points in the sky. So let's talk about these objects. You know, what kind of objects are we talking about?
Yeah, so back in the days, back in the 50s, when we detected the Milky Way, scientists started to become more and more interested in radio. And so we started building radio telescopes to observe stuff. And the very first things we found are objects called quasars. Quasars, the name comes from a quasi stellar object. So we detected stuff in the radio that appeared to be a point source, or appeared to be, you know, something that looks like a star in the radio, but it's not a star. And so it turns out that these quasars were supermassive black holes. So faraway galaxies, there are supermassive black holes in the center of the galaxies. And so as material get accelerated around these supermassive black holes, there are what we call jets. And so these jets would create synchrotron emission, and so synchrotron emission would create radio waves, and so we were picking up these radio waves. And so quasars were the first objects that were being studied using radio waves. And then a few years after that, a research scientist called Jocelyn Bell, and here this leads to essentially my research and what I do for a living. Jocelyn Bell in 1966 or 1967 was using a similar radio telescope to study quasars, to study scintillation of quasars, or, you know, because sometimes quasars can, or the light can interact with the interstellar medium, and, you know, she was studying quasars, and for some reason she was picking up a really weird signal, a really periodic signal that happened, that followed that had the characteristic that it was coming from a certain position in the sky. And so her trained eye noticed that. Like, she was, this is something weird. It appears to be astrophysical. Like, it's not someone starting their car engines, or, you know, someone using their microwave ovens. There weren't microwave ovens back then, but you get my point. And so that signal was super periodic. And so it turned out that this object was the first pulsar ever discovered. And yeah, probably I'll bounce it back to you, because I've been like, if I keep on talking. And
yeah, we'll continue on this, because this story is fascinating, very fascinating. There are reasons behind it that I want to spend more, us to spend more time on Jocelyn Bell here, because It's a very important history in physics, right? So let's talk about these quasars, because they are very interesting as well. We can't just pass it to pulsars. Pulsar is very important, but quasars, for our listeners, when we say they are quasi-stellar objects, because they look like a star. And you look at them at the first in the sky, in optical, they look like a star. They don't see, or even radio, they don't show any characteristics first. And when we talk about jets, then jets become beautiful. When you look at them in radio, they are just shoot out gas, you know, massive gases coming out of two sides. Either they're one-sided or two-sided, right, in the galaxy format. And they are extremely energetic. And when Val mentioned supermassive black hole, the supermassive black hole, just imagine that's a black hole with 10 to the power of 6, a million to 10 million, some, you know, solar mass. Take 10 million suns, squish it to a black hole, then you'll see a gigantic engine that can destroy anything around it. So this is what you see, those beautiful jets coming out, and you don't want to be close to that machine. So let's talk about these energy levels, because they are insane when you compare it to what we see on Earth, right?
Let's see. These objects are, you know, are quite luminous, even in the radio. Like, usually radio as a non-efficient way to transfer energy. So usually radio, that's why it's called, you know, low energy physics, because it's essentially a really inefficient way to transfer energy. But even in the radio, those things are you know, are super luminous. They are really bright in the sky.
So compared to our sun, Do you know exactly how many ergs are we talking about? Like let's say ergs in the radio format. It should
Yeah,
be a lot.
it's probably 10 to the 40 something, 44 maybe.
I think you're right. The ballpark 10 to the 40 to 45, right?
Yeah, I guess
And
that's
sun is 10 to the power of 33
yeah.
in a second giving us. So just listeners, put in your mind that it's 10 to the power of the 10 order magnitudes higher energies coming in radio. So we're not talking about the other energy.
Yeah.
There. And how far these objects are. That's one of the more important characteristics. If I recall correctly, the quasars are very far. That's why they're very interesting, right?
Yeah, they come from, halfway through the universe, if you want to, or maybe even more. Yeah, we see quasars. As you look further into the universe, you see backward in time. So this is another property, a nice property in astrophysics. So we see quasars that have been formed, after a few 100 million years after the start of the universe. So they are really far away.
So basically, Wael can see quasars that are 12 billion years old. That's what we want to get at. These are like fossils of universe. That it's insane that you get to time travel while sitting in your office right now. Look at something that emitted that light 12 billion years ago, and you see it right now. So that should make us feel small right there. And it's weird. This Back to the Future, right? Basically,
Absolutely.
In reality. Now let's move to Jocelyn, Bell, because now the story gets more heated. Now everybody's excited from quasars. Oh, everybody's trying to invest, and suddenly Jocelyn Bell comes and sees something just pulsing like crazy. And it was the pulsing. I think the pulse was very pulsy, meaning that very accurately pulsing at the same times, right? That's what got her eyes.
Yeah. So that signal was extremely periodic. And this was, back in the days, no one expected something like that. And so back then, Jocelyn Bell and her supervisor, they wrote a paper about it. And a few years after that, the discovery was super important, that a Nobel Prize in physics was actually given. But sadly, the discoverer of the object, the discoverer, Jocelyn Bell, was not acknowledged by the Nobel Prize. Only her supervisors did. Although later, let's say she was not recognized for that discovery.
That was very unfortunate, right? Because she actually was the person who discovered, and her advisor won the Nobel Prize, which shouldn't have been that way. She should have won the Nobel Prize. But recently, there was ceremonies for her justly for her discoveries. Now, let's talk about that pulsar, because it's very, very accurately periodic, like on point and on time. And as you said, it can't be a microwave, somebody turning it up and off and on, or a radio signal coming from her, unless the person is very accurately on time all the time, atomic level accurate, right? Because it's like an atomic clock level, very accurate in the period, repeating itself. So let's talk about that. Why it was repeating itself? What was causing this repetition?
So this was later, of course, when we studied pulsars more, we knew what was going on. So back then there was a bit of confusion as to what was causing these waves that people called them back then LGM, or little green men. But we were back in the 60s, so you can imagine how things were back then. But the point is, a few years after the discovery, we were certain that this object was a pulsar, because we associated that pulsar, or we associated that object, with a supernova remnant. Now here I can tell the big story, because we live in 2020. So what happens is that when a massive star goes supernova, so it just explodes, it can leave behind, because it's massive, it can leave behind either a stellar black hole or a small black hole, or it can leave behind a neutron star. And so black holes, they're interesting on their own, but we're not going to talk about black holes for now. If that object leaves behind a neutron star, that neutron star has a residual magnetic field line. So a neutron star is an object that's extremely dense. Like a teaspoon of a neutron star would weigh a Himalaya or something, like it would weigh mountains. And this is 1 teaspoon. And so there's a characteristic of neutron stars is that they have magnetic fields. So they are magnets, essentially. They are massive magnets. And so they have magnetic field lines that are spewing essentially from their sides. And because of the way the supernova remnant or the supernova happened, that neutron star becomes, it spins. So it's spinning at a millisecond sometime scale. So once every millisecond or something to a few, or one time to a few seconds.
So I wanted, this one is important with the listeners, right? The Earth goes 24 hours.
Yeah.
That's one spin, and you're often talking about a few milliseconds. But this object, a neutron star, can weigh up to 2 times the sun, more than that. And I think it's more than 2.4 if I'm right? It's Zwick's limit. You have to. Yeah. Is it true? I think up to.
Yeah, up to that limit.
Up to 2.4, they can weigh, let's say even 2 times the mass of the sun. That's insane to put them in a few miles. Yes. 5 miles maybe, right? Yes. 5 miles radius, something like that.
Yes.
It's very small. And then that thing with that much mass, in a lot of energy in it, rotates in milliseconds around itself. So that means how many spins per second. That's a lot. So about 1,000,
700, 500, 1,000 spins per second. So it's like your kitchen blender. So you've got a neutron star, which is a size of a city, weighing 2 times the mass of the sun, with 1 teaspoon of it weighing as much as a few mountains. That spins as fast as your kitchen blender. So I'm not sure what. If this doesn't blow your mind, I don't know what would. I mean, it's
exactly. That's why I wanted to zoom on this, because this is I would say neutron stars after black holes, maybe on par with black holes, are the craziest things in our universe. When they have they break every possible limit in the sense of size, mass, anything. And then now spin we are talking about.
Yeah.
So what happened with that spin? Is that spin helps you to get a very wild magnetic field, right?
Yeah. So the physics in neutron stars is such a way that you have a magnetic field line, and so if that magnetic field line is misoriented with the spin axis of the pulsar, right? So if that's the pulsar, let's say is just spinning in this direction, so the spin axis is upwards. So that's the spin axis. And so if the magnetic field line is misoriented, you can imagine, so now the magnetic field line as the pulsar spins would do some sort of a cone as it rotates, right? And so we mentioned half an hour ago that the magnetic field line can accelerate particles. And so these particles, as they accelerate, they emit radio waves. And so you can imagine the radio waves, there's a light cone that goes from the magnetic field line. And as the pulsar rotates, if you're the audience, if you are a radio telescope on Earth, you would see a small pulse as that magnetic field line or the magnetic field line hits your line of sight. And so this is exactly what Jocelyn Bell was seeing. So the pulsar was going for every spin period, Jocelyn Bell will see a small peak for every spin period. And so this was later coined one of the biggest discoveries in astrophysics. So that this is the pulsar.
Yeah, the pulsar is basically a crazy neutron star. So in order to imagine it, like, let's go, you're in an ocean and the light close to the ocean is spinning with a constant speed, and when it comes toward you, you see the light and goes away, you don't. That's how actually what was happening. A pulsar was, being in a way like that barely every time it was pointing, you would see a pulse. And how accurate it is in when we talk about milliseconds, right? because as far as I remember, they are very accurate, like an atomic clock level. They can be used as clocks in our universe, right? So is that how accurate they are compared to a normal clock we wear in our hand? Like, you know.
Yeah, they are way more, compared to our clock, they are way more, stable and accurate. I think the numbers here, if I'm keeping up with with literature, I think the numbers are between 50 and 100 nanoseconds. So this is, a few parts in, what is it, 10 to the power minus 8, I think. Yeah, 10 to the power minus 8 of a second. So this is this is damn accurate.
This is wild, right? Because like our atomic clocks are barely that accurate, and I don't think they're even that accurate yet. These things are now. The concept is why did I bring it this way? The pulsars become important in our universe, very important for some characteristics they have because of this accuracy in time measurements, right? This pulse measurements. Why can we elaborate on that, Val? Why they become very important in our universe when we look at the universe in general?
Sure. A few uses of pulsars is that because they pulsate, you know when they start and when they end. You can essentially use that pulsed emission to study the propagation path from the neutron star to the Earth. So this is like the very basic thing you can do with a pulsar. There's a big list of things you can do with pulsars. To me personally, I think the craziest and the most brilliant idea is to use an array of pulsars or multiple pulsars from different locations on the sky, time them really accurately, so know exactly when the pulsars are arriving, and use that to detect gravitational waves. I can elaborate on this.
Sure.
So gravitational waves are essentially waves in space-time. So space-time stretches and pulls, right? And so you can imagine if a gravitational wave passes through me, I'll be stretched and pulled, very small amounts though. I'm not talking about, centimeters, like it's a few atoms maybe wide stretches and pulls. But because space is being stretched, light would take slightly longer to traverse through the space, right? And so you can imagine if there's a pulsar at some location on the sky, and there's a gravitational wave that passes next to that pulsar or through that pulsar, the light that takes the pulsar to arrive to me on Earth would be slightly faster or slightly slower, right? And so because pulsars are extremely accurate clocks, we can measure that, right? We can know that there's a gravitational wave that passed through it. And so if you use multiple arrays or multiple pulsars on the sky, as the gravitational wave passes through them, that gravitational wave would have an imprint on the time of arrival of pulses from all these pulsars. And so we can detect gravitational wave with that. And to me, even as a scientist myself, as an astrophysicist, I still think this is a crazy idea and it's an extremely wonderful idea. Sadly, we haven't yet managed to find, but we are still searching. I don't work with pulsar arrays, but I hope that we can find a detection just because this is a brilliant idea.
Just to remember, I think it's I know a big team, because there's the first time for the audience, the gravitational wave was recently detected by LIGO, which is a gigantic interferometer in the state of Washington. And we have one in Louisiana and one in India and Japan are coming up. So it essentially what Val said, when these waves are coming, again, let's look at the water waves. Why I love water waves. They give you everything. You can analyze all the waves in physics on water, right? So pick two little balls and put them on a surface of a lake, a very calm lake, and then start spinning these things, right, around each other. That's one way to create, by the way, gravitational waves. So now as these two little objects are getting close to each other, what happens is by their rotation, they are giving you waves on the water. And now if you're sitting on the water like a piece of paper, the paper is going to get squeezed and, you know, let's just imagine extend it. It's not going to happen that way. But that is what's going to happen, because you're occupying the space-time, and the space medium is itself shrinking and opening. So you're going to shrink it. And if it is too close, it can rip you apart, by the way. So let's just hope they are always far from Earth and they're not going to do anything to us. And now what Wael said, so all of these arrays, now the second way of measuring gravitational wave would be insanely amazing to see that we can pick it from these things, because that's even a bigger, you know, because it shows the gravitational wave in the whole structure of the universe, right? Now, since we started talking about these things, right, you said the pulsars are very accurate. They come from different parts of the universe. By the way, one more cool thing I wanted to say was these, if you are one day, future generations, if you're listening to this, you're traveling in the universe, you're far from our galaxy, another use case for pulsars, they can act as a GPS. Because you know where in the universe they are, you can start going toward it. This can be your destination, helping you to keep up where in the universe you are, which I think that's a cool use case, but not useful right now.
You call them UPS, a universal positional system.
Yeah. Yes, exactly. Now, since we say these radio waves, not just pulsars, anything, they come through all the universe to get to us. Can they reveal anything else from the structure of the things that were between them, or anything about the structure of the universe as a general, you know, standing object?
They absolutely do. So a very interesting thing about radio waves is that as they propagate through electrons, or as they propagate through plasma, so this is a technical term here. Let's just call them electrons. You know, electrons are everywhere in the universe. Those electrons have a index of refraction. Okay, it's just like glass and water. If there's a, you know, if there's light propagating through water and glass, you see some sort of, you know, a visual effect. This is due to the fact that water has a different index of refraction compared to glass, compared to air. And so same thing happens out there in the universe. There are electrons, and those electrons have have a certain index of refraction. And so that index of refraction depends on frequency. And all I'm trying to say is the frequency of the light, or the wavelength of light, defines how the radio wave would interact with the electrons. And so this effect can be seen on Earth as dispersion. So dispersion is when when we observe a radio wave that it's emitted across what we call a wideband radio wave, right? So we emit something at a large frequency range. As the light traverses through the electrons, the higher frequency of light would be interacting less with the electrons compared to the lower frequency, and so the lower frequencies of light would arrive later to the telescope compared to the higher frequencies, right? And so we essentially see a dispersed signal. So a signal that, you know, if we have y-axis here, just imagine an imaginary plot here. My face is a plot, but we have y-axis as frequency, time as the x-axis. Frequency, you know, and time is increasing in this direction. A pulse that started somewhere in the universe would arrive on Earth following a dispersive sweep. So higher frequencies arrive first compared to lower frequencies. And so we can use this sweep, the amount of dispersion that the signal has undergone, to literally count the number of electrons that are between us and the source of emission. And pulsars do that amazingly well. We can measure the dispersion measure, so this is called a dispersion measure. We measure the dispersion measure, and then we can literally count the number of electrons between us and the pulsar. And so it will be great if we can do that so again, pulsars are have been only found within our galaxies because they are weak emitters. If we find an object that can emit pulsed emission from outside our galaxy, then that would be super great. And this would bring me to the world of fast radio bursts, or FRBs, and this is what I do for a living. But yeah, I'll bounce back to you.
Yeah, we will get back to fast radio bursts after this. But right now, just for our audience to understand, when that dispersion, you said they look like, it looks like a curve, right?
Mm-hmm.
A curved line. So let's just talk about the physics of that a bit, because that's very important to understand. When we say, okay, imagine you have a glass of water, right? Exactly. You have a pen inside. And you see the pen looks broken when you look at it from the side, basically. The reason is the velocity of the light inside the water is slower than it is in the air. So it breaks, if it was sharply coming down, let's say, it breaks by an angle, because it just goes slower right now. In order to keep the same velocity, it breaks, this basically the curve it was going. Now let's imagine you have multiple layers of deep glasses, very little thinness, right? And now the only way it will look like, since it's constantly breaking, it's going to look like a curve, right? So this is a very famous problem in math, by the way. It took them I don't know, there was a fight between Bernoulli, Newton, and everybody. They were showing off at each other, basically, on this problem. It's a very tough problem. It's not at all easy. But now, this curve is what Val mentioned, the dispersion, basically, or what is happening there because of the refraction indexing of each layer. Since we have a constant layer of electrons with different energies, right? So this is going to be, the velocity of these radio waves is going to differ when you pass through. That's why Val sees those curves down here. That can give him, what is the density? How many of these guys are blocking me up there, right? And now let's move to fast radio bursts, right? Because what is the fast radio burst actually even means? Why is it called fast, right?
Yeah. So just like on the small history here to link pulsars with fast radio bursts, we found the first fast radio bursts because we were searching for pulsars. We were essentially searching for pulsars coming from the small Magellanic Cloud. So it's a small galaxy that orbits the Milky Way. So a group of radio astronomers back in 2007 were looking towards the small Magellanic Cloud for what we call giant pulses. So pulsars, sometimes they can emit like a very, one of those pulses, can be like really giant, like maybe 100 or 10,000 times brighter than normal canonical pulses. So they were searching for these giant pulses. And so because they were searching for things outside the Milky Way, they started searching at the higher and higher dispersion measures, right? So because we already know that there are electrons in the Milky Way that contribute to a certain, let's say, X amount of dispersion, the authors or the discoverers said, all right, we have X amount of dispersion coming from our galaxy, but we need to search a bit more to look further outside the galaxy to search for the small Magellanic Cloud. And they were searching the small Magellanic Cloud. They were like sort of, pointing to different places. And then at some point, at the really far end of the small Magellanic Cloud, they picked up this really weird looking, back at the days, signal. It has a dispersion that is way larger than what we expect from the Milky Way, what is expected from the small Magellanic Cloud, and maybe halfway through the universe across. Like there was something weird about this thing. Like it appears to be coming halfway through the universe, and it's just an extremely giant radio pulse. And so what should we call it? Because it's a millisecond wide, it was like, all right, let's call it fast because it's a few milliseconds and it's a fast radio burst. And this is how like the word coined.
Yeah, so because it's really quickly happens, and that's why it's called fast radio bursts. Now, I know did they find what was causing this fast radio bursts? Right, that one. Let's start from the 2007 fast radio burst.
It's still a mystery to us. We still do not know what generates fast radio bursts.
So if we don't know the origin, that's when the controversy starts, right? Basically, as you said, the little green men were first coined as the origins of the pulsars, because it could be the actually little green men sending these signals, right? But now let's talk about that fast radio bursts. Are they repetitive like pulsars? Can they repeat, or they're just one-time thing only?
Yeah, well, yes, they can repeat. The short answer is yes, but they do not repeat periodically. So their bursts are not as periodic as pulsars. So pulsars, you know that after an X milliseconds, you have to see another pulse, whereas for FRBs, it's not the case. However, FRBs can have, or repeating FRBs can have activity windows that are periodic. What I mean to say is there's a source now, an FRB source that is really interesting, at least to me personally, is that every 16 days, there's a 5-day window where the chances are that you might find a repeat burst from it every 16 days. So it is not highly periodic, but the activity window is periodic, if that makes sense.
So why they become important for us physicists? We know it comes from far outside of our galaxy, far in our universe. And what can it teach us? What do we look for when we are actually detecting fast radio bursts?
Yeah, fast radio bursts can help us literally weigh the universe. They can help, these are cosmic tools, like cosmic balances that can help us weigh the universe. So if you remember a while back, I was talking about why pulsars are important, because they carry the imprint of whatever is happening between us and the pulsar. But the pulsars are within our Milky Way, and so there's nothing that, we already sort of understand what's going on in the Milky Way. But because FRBs are coming far away from the universe, they carry the imprint of all of these electrons between us and the FRB source. And so we can use individual FRBs to count how many electrons we have in certain directions. And this will become important maybe in the next question or so.
So yeah, because when we have this information, when we say about weighing the matter, the one thing right now is just the one question that rises here is: universe only made of what we see? Which I know most of people hearing this will know the answer is definitely no. So how much is the percentage of the universe made of from the matter we see around us right now? You and me are built up.
Yeah, it's pathetic, I would say. It's only 5%. So 5% of the universe, 5% of whatever, just look outside the window, look at the stars, look at everything that you see, your computer, whatever. This is only 5% of the universe that is made up of. And the more pathetic thing is that half of that 5% is completely invisible to us. And so this is why fast radio bursts are important, because those fast radio bursts can help us detect those, the other 2.5% of the universe that is completely missing to us or invisible to us.
So
again, just to iterate, this is not called dark matter or dark energy. So dark energy is 75% of the universe, and dark energy explains the expansion of the universe. Dark matter, on the other side, explains the rotation of galaxies, and that 5% is ordinary matter. The 2.5% of that ordinary matter, so they are matter that can be detected using electromagnetic light. We just cannot detect them because they are in some really weak state, in really dispersed weak state in material between the galaxies.
So let's talk about why they are, weak, because they are sitting between stars, between galaxies, the medium between. And since there's not too much energy going on there, they're cold, right? When they're cold, we talked about the emission back. When there's cold means the energies are low, so we don't get anything from them. Now, the only hope we have is something interacting with them. So we will see the missing part from that incoming energy. So I think that's where the fast radio bursts become important, because they come from very far away. So what is the situation now? Have they used these up to now to actually weight scale universe to see how big it is?
Yeah, there was a big paper that was published 3 months ago. So literally 3 months ago, and it claimed the first detection of the, of the missing ordinary matter. And it was a massive paper in the universe. A big paper in the FRB field, because the very first FRB that was discovered, we said, hey, we might actually use these FRBs to do this science. And so 13 years after that, some person, it's a bit sad. The person passed away actually a few days after publishing that paper. So it was a sad story. But before doing that, they solved one of the biggest mysteries in modern astrophysics.
That's fascinating. Yeah, because that missing part was bugging a lot of astronomers, actually. Now we get to the repeat. You said sometimes you can see them let's say, kind of repetitive signals. There's, you're working right now as a postdoc in searching for Extraterrestrial Intelligence Institute. So why the SETI is getting interested in FRBs? Why do we think this can lead us? There's a chance, right, that this can lead us to extraterrestrial intelligent beings,
Yeah, absolutely. I can attack this question on two different sides, I would say. The very first one is the instrumental part of it. So searching for pulsars, searching for fast radio bursts, studying pulsars, studying fast radio bursts, and searching for ET, they all share the same technical, if you want, technical difficulties, and like the same processing of the data, the same massaging of the data you have to do is the same for all of these sciences, right? And so because we know already that FRBs, we know that we can detect FRBs. We can sort of use FRBs as a proxy or a way to test our instruments, to be able to, to be sure that we can search for ET. So this is one way why the SETI community is interested in fast radio bursts. The other way is that, or the other reason why the SETI community is interested in fast radio bursts is that they might actually look like a signal that might be broadcasted by ET. So a impulsive millisecond wide flash in the radio, it could be a beacon. And so I personally do not think FRBs are, or this particular class of objects, which are FRBs, are, because of many reasons. But that doesn't mean that a similar signal might be due to ET. And so this is why all the communities, the FRB and the SETI communities, are collaborating on technical on technical problem solving, and at the same time on the science behind FRBs and SETI.
Yeah, so because for our audience, whenever an FRB is repeating itself and we don't know the source, sometimes there's always that alien option available, right, to explain these things. The reason is because maybe these extraterrestrial beings like us are advanced, and they have radio signals, right? Very strong radio signals, which I think, that's one, way of looking for beings, because it's just one thing I always thought myself, that this is only one data point, life, for us. We know we can communicate in radio. We don't know, this is only one point. You can't fit a line to it and say everybody else have to emit radio, or everybody else has to be the same as us. Maybe they're going to be very different in the way they communicate, which I think, I would like to ask this question from you, Wael. As an astronomer, do you think we are alone in this universe? What do you think?
In my personal opinion, it would be super egocentric way, or we'd be super self, I can't find the words here, but it's an egocentric way to think of things if we were to think that we are alone in our universe. The universe is massive, right? We're talking about 10 to the power, I can chop it, throw in some numbers here. Number of stars in our galaxy alone is like 10 to the power 11 stars. The number of galaxies in our universe is another 10 to the power 11. Just multiply those two numbers together, you get a 10 to the power 22 stars in the universe. That number is actually bigger than the number of sand grains on Earth. So you can imagine how many stars there are in our universe.
And we didn't add planets, right?
Yeah, and even a single, let's say just very simple. Yeah, you're absolutely right. Just a single planet orbiting every star, we end up with 10 to the power 22 planets out there. So the chances are that we are the only civilization, or we are the only, I would say, intelligent civilization here in quotes, that lives in this universe. I think this is just madness to think that we are.
Yeah, regarding the part that, it is actually next to, I think from my mind, when you put it statistically, it's next to impossible to be the only beings on this universe. Because if you disappear Earth tomorrow morning, nothing is going to happen to universe. It's just going to be like, okay, another small dot gone, because there's no, we are not at all significant by any means, So let's go back to your work right now, your research, right? Which has been like on FRBs. What kind of surprising results have you seen in your period of working on FRBs?
I think the most surprising to me personally, because it was one of my discoveries. I found an FRB that had a triple peak structure, right? It's in a way, it's characteristic in a way that it sort of repeats itself within a few milliseconds, right? So it goes bam, bam, bam 3 times, and those 3 bursts look really the same. And so we can estimate that this signal is coming halfway through the universe, and for it to be far away, it needs to be super bright again. So it has to be super luminous, and it has to be super energetic. And so to me, it's super incredible that a signal that emits 100 days worth of the sun, sun's energy in 100 or 1,000 days, back in 1 millisecond, and repeats itself that quickly. It doesn't have enough time to recharge, right? It just goes bam, bam, bam in 3 milliseconds. To me, that still blows my mind. And I hope within my lifetime here on Earth, I hope we can get to an answer, because that'll make me sleep better.
You don't know what was causing this, right? That's insane. The amount of energy and the short span of this. Again, we can put the ET as the possibility. I'm just joking. As always, when something we don't know, public will fill, basically newspapers would fill that gap with aliens quickly. And 3 days later, scientists will remove that, from the gap and fill it with something else.
Well, I mean, just as a disclaimer here, we currently here on Earth have the technology that would allow us to send an FRB-like signal to halfway through the Milky Way. And so it's not purely impossible that FRBs can be originating from aliens. It's just that, in my personal opinion, there are different reasons why it might not be the case.
Yeah, I'm just saying it's one of the options, but not always the option. That's what the media sees the FRBs as most often. That's the only option for them to explain this. But being honest, it's one of the options. And as you said, it's quite possible that we've been detecting one when we don't know even, right? Yeah. Now, I want to switch gears, unless you have other, if you want to explain more about your research. I want to switch gear to what happened that Wael got interested in science in first place, because maybe it will be interesting for our listeners who are thinking about a career in science to become a scientist. What triggered you, Wael, to be a scientist, or specifically why you became astronomer? That's the
it's a typical question on a job interview or whatever. And I sort of answered the similar answer, and it's not the most interesting question, most interesting answer usually on my side. But I was, as far as I can remember, I was interested in astronomy. So I was interested in math and physics in general, and in particular astronomy. This is how I grew up. Like this is as far as I can remember. And the other reason why I wanted to be a scientist, because I knew I couldn't do anything else. I was bad at school with everything else. I had really good grades in math, physics, a bit of chemistry, but like otherwise I was just a complete, just, I'm not gonna say the word, but I was pretty much physics and math is all I can do. So I just decided to follow this path. But yeah.
Cool. So I always ask from other fellow astronomers. I remember when I first time went to actual observatory, right? I was undergrad, and I saw Andromeda galaxy on a 2.4, on a 60-inch Cassegrain-Schmidt telescope. This is my first time seeing Andromeda, and I'm around 18, and I grew up imagining becoming a right astronomer. And when I realized I'm looking at 2.3 million, light years away, and this light took 2.3 million to get to me, and I'm actually seeing it, it was a very weird feeling for a couple of days. I want to see, how did you feel when you first walked to an observatory that magnitude, and then started getting data and started to looking at it on your screen?
Yeah. So for you, I think Andromeda was your first love. To me, I think Saturn was my first love. But I was probably maybe a bit younger. So probably I was 13 years old, I think, when I first saw Saturn's rings on the small telescope. I don't remember what the telescope was, just a small amateurish one. And yeah, to me, yeah, I get this, I would say, an overwhelming feeling of how big our universe is. And, that's, to me, all these unanswered questions. I know I won't be able to answer. But to me, a life goal would be at least to try and understand something about it. And I think this is sort of my motive.
It is interesting, yeah. Just because always I ask this question, because everybody has a very different type of feelings for a while. Like you feel. I would say astrophysics is very humbling. When you walk out of your observatory, you're like, you feel very little, actually, really very little for next couple of hours when you came out of your observatory. Now, what would you suggest for people who actually want to become scientists in the future? How should they approach it? Like if you go back to the same age, and if you want to give yourself an advice, Val, do this. It's gonna make your life easier to become a scientist.
Yeah, I think don't fall for the stereotypes of that have been sort of fed to us about science and about scientists in general. One thing I wish I knew when I was little or was young was that scientists are actually normal human beings. I talk to a lot of people, and people, when I approach them, or they just don't think I am a scientist. I don't look like a scientist. I don't speak like a scientist. I do other things in life, and so this stereotypical image of what a scientist looks like is something I really hate. Another thing is it's something we're trying to improve in science in general and in astronomy, is gender balance. We need of course gender and race balance in astronomy and science. We need as diverse people as possible on the team to do science. So don't let any of this stop you from doing science, neither the stereotypical image of a scientist, nor from where you come from or who you are. And I guess that That's
Yeah,
how I would
exactly.
say it.
The gender part is very actually, exactly the story of Jocelyn Bell when we were talking about. So how disappointing it is. I hope
Yeah.
it doesn't happen at all anymore, ever, because we have very brilliant scientists that get disappointed because of these things, or brilliant people who get disappointed by these stories that if we pursue science, somebody is going to steal our ideas, our work, and actually the community will praise it. That
Yeah.
was, I think, the disaster that happened back then. The
Yeah.
community actually stood beside and behind this decision, right? Hopefully it will never happen to anyone again. And so the other thing I want to talk about, like you said, I always open this up, scientists are humans.
Yeah.
Right? That's a very important sentence here.
Yeah.
So how do you spend the rest of your time when Val doesn't do science? What else he does?
Um, a few things. I used to go to the gym, for example, every day. So to me, weightlifting was part of my daily activities. I don't look like it, at least right now, because the pandemic and all the mess that's happening around the world right now. I'm also a pianist. I play the piano on a consistent basis. I love dancing. I'm a Latin salsa dancer as well. Um, yeah, I do a lot of activities, and yeah, and I always enjoy people's reactions to when I say I'm an astrophysicist, and they'd be like, scratching their heads and like, why aren't you, looking at a telescope? Why are you here right now? Sort of reaction, but you know what I mean.
Yeah, exactly. This stereotype is, not just for astrophysicists, any other type of scientist, but more for astronomers. I noticed, being honest, physicists, they get a lot more because the TV loves to stereotype physicists. Now, since I've been asking these questions from everybody to just, talk to people who are listening to this podcast, hopefully, that right now everybody's locked down, right, sitting at home. I would say we physicists are really good at isolation. That's just, I want to say it outright. But what would be your suggestions for people who are in isolation right now in pandemic? What can they do to make themselves, more active? What would be your suggestions, Val?
Look, we live in a world. We live in a really connected world. We live in a world where we can get information in like a click of a button, and we should be, we're privileged for that. Like if you were living back in the days where the Spanish flu was happening, I can imagine people sitting at home just doing nothing. Whereas we have the resources to do like literally anything we want. Being behind the computer screen. So to me, a small piece of advice is to try and search for new, a new passion. Watch YouTube videos. YouTube videos are extremely beneficial, extremely educational. Um, watch podcasts of people talking about their work. Try to connect with, even if it's one-sided, try to connect with other people around you. Yeah, try to learn as much as you can, because this is an opportunity to learn more about yourself first, and to learn more about the universe.
That's awesome. Now, I always ask this question as the last question because this is for me. I really like to know this question's answer. The question is, what book in your lifetime, when you opened it up, you put it down, you went, wow, what just happened?
That's a I'll have to admit here I'm a bit guilty of this, but I have not read books recently. I think when I started my master's, because I had to read a lot of research articles, and And so I wanted a reason like to get away from reading anything else. And so it's not sort of part of my hobby list.
Even if you go back to your high school time before
Yeah.
masters, it always, there is some piece of text you read and you become like, wait a second, this thing is hitting me.
Yeah. That's
Even if it is physics, though, I tell you, I open it to physics textbooks always too.
I think one of the I would say a small like booklet about Stonehenge. And so when I first read it, like I opened it, it had this massive like giant map, and then and this is a really small thing, I guess, but like maybe now that I look at the incident, or remember the incidents, I was like, okay, I probably wanted to be a scientist since then, but I was really intrigued by what I was seeing and reading, and like the history and the culture of that place. And yeah, I guess that's it. But it's not the most interesting answer, I know, Reza, but
Oh no. That's the reason I asked this. Even as you said, a small text, it doesn't matter how big of a book it is. Sometimes a very little manuscript can make you go like, wait a second, what just happened after I read it? So Stonehenge was the one that you actually, when you read a small piece about it, what did it hit you when you read that?
It's multiple things. It's I guess the mere fact that science and maybe astronomy as well is embedded in science in general is embedded in culture and probably religion as well. To me, that was the enlightening idea that how important science is, because it's part of us, right? It's part of our culture. It's part of our history. And so the fact that those prehistoric people were actually thinking the way that they were thinking, and they built this structure that really needed physics back then, like transporting these big rocks and putting them in a certain way, like this needed people to like think about it really properly to do something like that. And so I hope my answer makes sense.
No, it does. So the other question I would ask you, since you love music, I see that you're a pianist. Uh-huh. What is the most favorite piece of music you listen to? Because
I'm a classical pianist. I like a lot of Chopin's pieces. I try some of Chopin's nocturnes. I love the fantasy impromptu. I guess that's personally my favorite piece, because it sort of combines the craziness and the pattern. So the craziness of a sort of a technically demanding musical piece, and the pattern that you can follow in one piece. I guess to me that's my cool. Personal. Yeah,
that's awesome. I will put the links to them just under the description. The last question is, where can they find you, Val? If somebody wants to find more about your work or find you to ask questions from you, where can they find you?
Yeah, sure. I can probably share with you my Instagram account. I'm not very active on Instagram. I try my best to be. My Instagram is the bearded astronomer, for obvious reasons. And I have a small website as well on the SETI Institute. I can send you the link to that as well.
That is awesome. Thank you for agreeing to being here, and it was really nice to talk to you.
My pleasure, Reza. Thank you for inviting me onto your podcast.
Thank you.